everything is accomplished. So this is going to be our introduction to our second kinematics motion equation for acceleration. And we want to start off by looking at our learning goals. And they are that to determine the acceleration from a velocity versus time graph, to determine change in position from a velocity versus time graph, and then you also want to be able to calculate any unknown using the equation that we have here. This extra a right there. So we want to be able to do those for this particular equation. So we want to start off by reviewing the variables that we've already introduced, and those are time. Time is the measures the interval between events and is generally measured in physics class with a photo gate, although we still do use stopwatches in certain cases. A photo gate is a much more accurate way, so when we can, we want to use that. Because time isn't really affected by a lot of things, we generally say that time is almost always the independent variable. In fact, in this class, there's going to be no experiments that we actually have time as a dependent variable, because we're going to have you can't change time in any particular experimental setup that we do. So because of that, we can go ahead and go from there. We can say, well, what about velocity? Velocity, once again, is a thing that we've already talked about. And in the lab that you did, we also experimented with velocity in terms of two different velocities. So we talked about an initial velocity as determined by photogate A, and a final velocity as determined by photogate B. We said you can determine the initial velocity of the marble, or how fast it's going at the first gate, by taking the diameter of the object, marble, car, whatever, and that's the top. Remember, we need to put it in meters. And then the time A is the time that it takes to go through photogate A. And then the final velocity can be done with the same formula, but by using time B instead of time A. Now, velocity can only be measured indirectly. You can't actually directly measure velocity. Instead, what you're doing is you're looking at a combination of things. Either what you do is you use a photogate and a ruler, and you're measuring meters and seconds independently, or you can use something called radar or LiDAR to measure the velocity by looking at something called the Doppler effect. And actually, LiDAR works a little bit differently than that. But basically, you're measuring other things and using them to determine velocity. So you're not directly measuring velocity. Acceleration. Acceleration is new for this particular thing. It is the rate of change in velocity. Now, just like velocity is a vector, acceleration is also a vector, which means that it has to be defined by both magnitude and direction. So you have to say it's 10 meters per second squared east. You can't just say, oh, 10 meters per second. It won't work that way. So acceleration is a vector. The standard units of acceleration are in meters per second squared. So it's a kind of a rate of how quickly you're changing velocity. So whether you barely step on the gas pedal or you really hit the gas pedal really hard in order to try and get where you're going. So, like we said, acceleration can be positive, it can be negative. So, just you have to be very careful when you're looking at things like directions. Now, examples of acceleration. An example of acceleration is stepping on the gas. Generally, that indicates a positive acceleration, depending on what you define as positive. But generally speaking, when you step on the gas, you're increasing your velocity, so that's generally a positive acceleration. Now, you also have when you step on the brake. When you step on the brake, you're also accelerating, except you would be considered to have a negative acceleration. A negative acceleration is also called a deceleration. So whenever you look at this, you have a positive acceleration and you have a negative acceleration. But there's another type of acceleration that you have as well, and that's the acceleration that you have whenever you change direction. Like we said, acceleration is a vector, and so since it's a vector, whenever you change the direction of something that is going, you also have a change in velocity and therefore an acceleration. So turning the wheel means it's a situation in which the velocity, the magnitude doesn't change, but the direction does, and therefore same, but direction changes. And that is also a form of acceleration. So anytime you change how fast it's going, now a lot of people get these terms confused. This idea of velocity and acceleration, they mix them up. Now they really don't have a lot in common. All they really have in common is the fact that they are rates. They're rates of change and they're vectors, but they measure totally different things. Velocity is measured in meters per second and is how fast. Acceleration is meters per second squared and is a measure of changing velocity. So really they're completely different things. Yes, they can both be positive and negative and zero, but really they're entirely different things. You can have a velocity of zero and have some sort of acceleration. You can have an acceleration of zero and have some sort of velocity. They really don't have much to do with each other. So I'm not quite sure why people get them so confused, but they're very, very distinct topics. Now, from the investigation, we actually found that you can figure out quite a few things whenever you're taking a look at um, a velocity versus time graph. We said that the first thing that you can determine is you can actually pick any 2 points on a straight line and you can determine the slope of that. And when you determine the slope of this line, you would take velocity, change in velocity, divided by change in time, and that would give us our acceleration value. And you see that work done right here. Okay, change in y over change in x, and what it does is it gives you this 2.5 meters per second squared. But we also said that not only can you do that, but you can actually find the area under the curve. So let's say in our case we wanted to do it at 5 seconds, or at 10 seconds, excuse me. You draw a line down at 10 seconds, and what you notice is you notice this triangle. Well, the triangle is really useful in the fact that it indicates the shape of, or the area that we're trying to solve for. You're always trying to solve for the area under the line. Sometimes it'll be a rectangle, sometimes it'll be a combination of shapes, but in this case we have a triangle. So the area of a triangle is really easy to calculate. It's 1/2 the base times the height, where we have the base is 10 and we have the height is 25. So we do 1/2 of 10 times 25, and we should actually get our value as 125 meters. So it's just kind of something that shows you that you can get both displacement and acceleration from a velocity versus time graph. So we come to our first example, and you need to be real careful when you're given some sort of narrative that goes with a graph. People tend to focus on the graph, rightly so, because the graph gives important information, but a lot of times you see information that's really important in the narrative as well. In this case, the car starting at -20 is going to be a significant piece of information that we really need to be able to use. So if you look, normally we think of objects as starting at 0 and going in one direction or the other. But in this case, it's saying that you start at -20 and then you move in this direction. So it says, what is the final position of the car? So remember, position is related to displacement. In fact, displacement is your final position, we'll call it final position, minus your initial position. So if I have an initial position, if I can find my displacement, that would allow me to calculate my final position. So really what we need to do here is we need to go ahead and calculate what our displacement is going to be in this particular case. So if we look, we draw a line down where we're looking at the graph. So we have a graph right here, and then we have kind of an odd shape. It looks like it's almost a triangle, but it's not quite a triangle because of this right here. It's kind of missing whatever that is. So since that's not there, we can't use the formula for a triangle. Instead, what we need to do is we need to take this shape and we need to be able to split it up into different geometric shapes that we do know the formula for. So the first thing that we want to do is we want to go ahead and draw a line right here. And when we do that, we now have two very distinct shapes. We have a triangle that we can find the area of using the formula 1/2 base times height. And in addition to that, we have a rectangle that you can see right here, and we can calculate the area of that shape as just base times height. So we'll start with a rectangle because that's the one we've got here, and you have a base of 6 and you have a height of 5. So that gives you an area or a displacement of 30 as far as the rectangle is concerned. But we're still not quite done in the sense that we have this triangle that we need to take care of. So we do 1/2 the base times the height again. Once again, the base of the triangle is 6. And here's where some people get stuck. They say, oh, the height of the triangle is 20, but it's not. Remember, we started the triangle here, not at 0. So the triangle is actually going from 5 to 20, which is 15. So here's 15. You have a base of 6, and you multiply it by 1/2. Whenever you do that, you get 45. And so you get a total of 75 meters. Now remember, that's not actually your answer. In this case, what it is that represents the displacement. You have to take into account the initial position. So what I'm doing is I'm starting at negative 20 and I'm moving 75. So what that means is I'm actually going to end up not quite nearly as far as I thought I was going to be. If I move 75 from here, I don't end up at 75. Instead, I end up at 55. This question says, what is the acceleration of the car shown right? So once again, we have the same graph, but instead of asking for the displacement or something along those lines, instead what this graph is asking for is it's asking for us to determine the acceleration. Remember, the acceleration is determined by the slope. It's the change in velocity over time. Remember, for a straight line, you can choose any two, any 2 points on the graph. So you could choose the first 2 points if you wanted to, but then you'd have to be real careful editing, or determining what that point would be. So that might not be your best choice. So instead, you might want to look at some other options. I'm going to choose this first point as 0, 5, but I'm going to choose the second point right here on the end. It's going to be the point 520. And the reason why I chose that point is it's the easiest one to see on the line. So if we were to do that, we can now say my 2 points are 0, 5, and 520, so we find the slope. The acceleration is the slope, or change in y over change in x, which is 15 over 5, which gives us 3 meters per second squared. You should be able to use this graph and determine the initial velocity to be 5 meters per second entirely on your own, and you should be able to reproduce something like this on a quiz. So finally, we get to what we actually looked at in the lab, and that's actually measuring acceleration. We actually introduced the concept of acceleration in the lab by measuring the change in velocity. So once we identify the fact that there is in fact a change in velocity, we say, okay, well, how quickly is it changing velocity? And so we say, okay, we take our two velocities and we divide it by the time. And we actually did this in the lab by taking diameter divided by time b, diameter divided by time a, and took the whole thing and divided by time AB. So that's our equation, which you can see here. Acceleration can also be measured in other ways. You can use two photo gates and a meter stick like we did, but there's actually something called an accelerometer, which can be used to indirectly measure acceleration again. Now you can find accelerometers in a lot of devices that you use commonly, including Wiimotes and PlayStation 3 controllers, iPods, iPhones, iPads. If you've ever seen it where it kind of tilts on its axis, or you can swing it like you're throwing a baseball or something like that on the Wiimote, those are all examples of things in which they're using the accelerometer to measure what's going on. If you've ever played Wii Baseball, you can cheat really quickly or easily by, instead of throwing the baseball whenever you're pitching, you just kind of flick it with your wrist. And when you flick it with your wrist, what you're doing is you're having a great acceleration because you're changing velocity a whole lot in a short amount of time, and that registers as throwing a fast pitch on the game. They're also found in digital cameras for stabilization and navigation devices as well. So accelerometers are in a lot of devices that we use commonly today. So here again, you see the equation. The equation right there is A equals VF minus VI over T. And so we've introduced a new variable, and that's the variable A. So we're going to start off with that. We say A is acceleration, and it's generally defined as the rate of change in velocity. Now the SI unit is the meter per second squared. Now a lot of people get confused with meter per second squared and just meter per second, but really they're different values, and it's measured with an accelerometer. Now you should know what final velocity and an initial velocity are, and you should be able to plug those values in. If you don't know what they are, refer to your notes from the previous unit, also time as well. So we go to example B1. It says a ball accelerates at 10 meters per second squared, coming to 20 meters per second in 4 seconds. What is the initial velocity of the ball? And then it asks you to go ahead and work that out for the initial velocity. So if we look at our information that's given to us, we're given an acceleration of 10 meters per second squared. In addition to that, we're given a final velocity of 20 meters per second. We're also given the time as 4 seconds, and we're asked to solve for VI. If you look at our equation is A equals VF minus VI over delta T, or 10 equals 20 minus VI divided by 4. So the first thing that you should notice is that whenever you do this, you get multiply both sides by 4, and you get 40 equals 20 minus VI. And that kind of throws some of you off to begin with, because you're like, well, how are we going to do this? Generally speaking, people are taught not to move the variable. You can move it if you want to and if you're comfortable with that. But what I'm going to do is I'm going to subtract 20 from both sides. And when I do that, I'm going to get negative 20 equals, positive 20 equals negative VI. And now, you generally don't want to have that negative VI there, so we multiply both sides by negative 1. And when we do that, that's when we end up with negative 20 equals VI. And people usually have a hard time dealing with this. Well, how can the initial velocity of the ball be negative? That doesn't make any sense. Well, remember, the initial velocity of negative 20 meters per second just means that the ball was moving this way to start, and then now is moving this way. So it just changed its direction. And so it does make sense to have a negative initial velocity. In the next example, it says determine the acceleration of a boat. So you're looking for A, that accelerates from 10 to 30 meters per second in 2 minutes. So whenever we look at it from this perspective, what we can say is okay, I'm looking for A, the initial velocity is 10, the final velocity is 30, and then the time in this case would be 120 seconds. Remember, we don't deal with minutes. You have to convert minutes to seconds. So the equation is A equals VF minus VI divided by delta T, or in our case, we would have A equals 30 minus 10 over 120, which would be 20 over 120, which you can simplify to be about 1/6 by crossing things out, or you can go ahead and put it in your calculator and figure out what 1/6 is. You should be able to solve example B3 using the method that we talked about in terms of picking out your given, plugging it into the equation, and you should be able to get that the acceleration of this car is 3 meters per second squared entirely on your own.